We're gonna move on to 7.4. So I am jumping around a little bit. The reason why I want to go to 7.4 is because when we're looking at inverses, we were essentially doing what this section is asking us to do. So remember, when we first started, we were given a radian or degree, and we have to find the terminal point. When we did inverses, we're doing backwards. So we're using the terminal point and trying to find the radian. But with these trig equations, it's going to be the same. There's not inverses aren't going to be involved. So the restrictions are not. That's the big thing. The huge difference here is there are no restrictions other than the original domain and original range for sine, cosine, tangent, all our trig functions. Those original domain and ranges still apply. But the ones that we restricted for inverses are no longer applicable here. So the idea is we're going to be given, right? We're looking at, and we use our unit circle to help us. We're going to be given terminal points, and we have to find the radiant. So this point is given, but the radiant isn't. Now, something that we have to be careful with when it comes to doing these equations is this same exact terminal point can happen in two different places. If we're talking about, let's say, for example, the y coordinate of that terminal point. So these two y values are equal to each other. So we have to take all these into account. And the problem is, well, it's not a problem, but something that we're going to have to be aware of that we didn't have to think about when it came to inverses was, now I'm trying to find every possible solution, because when it comes to looking at equations, there's multiple solutions to one equation, but there's only a couple unique solutions. So when I say that, it's because I can get back to this exact same position, right, by rotating all the way around the circle. And we can luckily do this rotation an infinite number of times. So because we can do this rotation an infinite number of times, this position with this terminal point has an infinite amount of degrees or radians associated to it. So it's something that we're going to have to put some thought into. But in terms of finding our solution, it's going to be the same as we did for inverses, that you're given a terminal point and you're supposed to find the radian or degree that's associated to it. So let's jump right in. Solve and write a general solution. In some situations, you might only be asked to find the solutions that are within one rotation of the unit circle, or within one interval, depending, because I'm not going to always refer back to as a unit circle, but we might refer to an interval versus an infinite interval where there's an infinite amount of solutions. But even in those infinite amount of solutions, there's really only a couple unique positions, but you can get to that position an infinite amount of times. So our first example, we're going to keep it quick and light. Just like any other type of equation, your goal is to isolate your variable. But I don't want to apply my inverse property in this situation, because if I try doing the inverses, and inverses end up creating a restriction. This problem didn't start as an inverse. It started as a cosine, where the examples that we were doing before started as inverses. So the restrictions were right from the beginning. This has no restriction whatsoever. This is just asking for where is cosine equal to 1/2. But there's a couple things we can get from just looking at this isolated trig function. And that is that it's positive, right? And we know cosine is positive in quadrants 1 and 4. And if I was going to find my answers, I know it's 1, 2, 3, 1, 2, 3. But remember, when I say 1, I really mean 1/2. When I say 2, square root of 2 over 2. When I say 3, I really mean square root of 3 over 2. Now, because we're talking about cosine, I know cosine always pertains to the x. And the 1/2 is this 1. So I know I get 1/2. I get 1/2 at this particular angle is pi over 3. But because I'm looking at the x-coordinate, I know there's an exact corresponding x-coordinate in the fourth quadrant as well. Now there's a couple ways to illustrate this quadrant. We can illustrate it as negative pi over 3, or starting from 0, we can rotate all around the circle. And remember, that's going to be 3, 6, we go back 1. This is going to be 5 pi over 6. But this is a part where 5 pi over 6 and negative pi over 3 are the exact same position. Or sorry, I made a mistake. It's not 5 pi over 6, it's 5 pi over 3. So even though 5 pi over 3 and negative pi over 3 are the same position, one took a much longer path to get there. So they are different solutions, but the position is unique. Luckily, I know that I can, and then I can still continue after 5 pi over 3, I can still continue rotating and getting back in the same position. Same with negative pi over 3, I can rotate in the clockwise direction and go back to that same position. Now, as for pi over 3, it would be difficult for me to get from pi over 3 to negative pi over 3 and then to go right back to this next position to illustrate that as a general solution. So in this situation, we break down our solutions into, so we're going to choose 2 thetas. But we're going to break down our solution into 2 parts. Pi over 3 and 5 pi over 3. Or you can use negative pi over 3 as well. Now, the idea is, remember, I can keep rotating an infinite amount of times and get back to this exact same position. But if you notice, I am rotating one complete circle. Hence, I know that all I'm doing is I'm adding 2 pi, one full rotation to get back to the same position. And then I can keep doing that again and again. I'll have to go 2 pi, but then if I do it again, that'll be 4 pi, 6 pi, 7 pi, 8 pi, 9 pi. And essentially, I can either add 2 pi or 4 pi or 6 pi or 8 pi. But this is just the same as saying 2 pi times 2. This is saying 2 pi times 3. This next one is saying 2 pi times 4. The first one is just saying 2 pi times 1. Or we can say plus 2 pi times 0, just giving us exactly pi over 3. And this is just 0, 1, 2, 3, 4. And if you notice, that's where we have to add our k. But if you remember when we did our domain, we would write, I'm going to do the same thing for the 2 pi over 3, the 5 pi over 3. But in both of these scenarios, k is an integer, right? This just means element. It's the way I like to write it. But in other words, I'm just saying where k is an integer. You can say either one of these. You can either say this or this. Either one. They mean the same thing. Right? Because I can also go, I keep rotating in the counterclockwise direction, but I can also rotate in the clockwise direction. And that's where I need it to be not just a whole number, right? 0 and all the positive numbers, but I also need negatives as well. And that's where an integer is useful. And this would be my general solution. Now, if I was only asking solutions from 0 to 2 pi, then I would only have pi over 3 and 5 pi over 3 as my solutions. In every other situation, every other equation is going to be exactly the same as that first one. The only thing that's going to make some of these problems a little more challenging is the introduction of some algebra. All right? So the goal here is we have to isolate our trig function. How do we do that? We subtract square root of 3 on both sides. That leaves with 2 sine theta. I divide my 2. And then I'm back in the same situation as that first problem, where I'm trying to find the general solution for when theta gives us these answers. But I can do the same thing I did before. I can remember 1, 2, 3. And I need square root of 3 over 2, so I need one of these 3's. But that happens, sine, we're talking about the y coordinate. So that means we are looking at all these outer ones. And the one I need is going to be the 3. And that is because 3, or when I say 3, I really mean square root of 3 over 2. But let's not forget, this sign is negative. So that means we are looking in quadrant 3 and 4 for our solution, because that's where the y-axis is negative. But once again, so that means I'm looking at this position, but I'm looking at it in quadrant 4 and in quadrant 3. Remember, the one that's closest to the y-axis are our 3's. So I already know from the previous one, this is 5 pi over 3, right? This is doing a full rotation. That's 5 pi over 3. Going from 0, right? And these are the two positions we're focused on. Let me highlight them. I'm not worried about the pi over 3. These are the two positions I'm focused on. So I start from 0, and to get to the same position, that's going to be 1 less, right? So that is 4 pi over 3. Because the 3's divides the top into 3 equal pieces, the bottom into 3 equal pieces. So this is 1, 2, 3, 4, 5, and then 6. So 4 is here. And just like before, I want a general solution. So I have 4 pi over 3, 5 pi over 3. And if there was a way for me to just get to the next solution, instead of writing 2 separate ones, it would be nice to write 1. But because the distance between them are different, there's a shorter distance and a longer distance. So it's easier to just split both of them up, because it's easy to go from 5 pi over 3 and just say add 2 pi, get again, add 2 pi again, add 2 pi, or subtract 2 pi and subtract 2 pi. So we're adding 2 pi k to both of them, right? And we're saying that because k is an integer. Because we're getting to that same position, we can again and again and again and again and again and again. And I'm doing that by doing one full rotation to get back to that same exact place. So that makes it a little bit nicer to do. Now, what I said, what's going to make some of these problems a little more challenging is adding some additional algebra and creating a situation that might be a little more challenging. Because at first hand, my sign is isolated, but I'm confused with this 2 that's being added here, right? Because we see theta and we think, okay, we have to find the theta that gives us 1/2. Be careful, because let's not forget, this entire argument is what's going to give us 1/2. Not just our theta. We will find theta, that's what we're looking for. But when you're thinking of this equation, you're thinking of this 2 theta all on its own. Where does that give me 1/2? So in other words, or you want to think about it as sine of this new angle is equal to 1/2. Visualizing it this way, it takes the critical portion of this 2 theta, and then I can just do exactly what we were doing before, where we're trying to figure out where do we get 1/2 for sine. Once again, 1, 2, 3, 1, 2, 3, and now that's going to happen at the 6's. Remember, the ones that are closer to the x-axis are the one I like to call the 6's. And we are looking at quadrant 1 and 2, because that's where sine is positive. So I have this solution, which is pi over 6. And then I have the second solution, which is, if I go all the way around to 6, 1 less than 6 is 5. So it's at 5 pi over 6. Now, that's when sine is equal to 1/2. But that's not when 2 theta is that theta is different than here. So what we need to do is but we know that sine is equal to 1/2 in 2 places, at 5 pi over 6 and at pi over 6. So this is the outcomes we need in this argument to ultimately get a positive 1/2. So what I do, I'm just going to set my 2 theta equal to where I'm setting it equal to when sine by itself is equal to this 1/2, and it happens at 5 pi over 6 plus 2 pi k, because it happens every full rotation, right, to get back to the same position. But I'm ultimately trying to solve for theta. I'm not trying to find just when sine is equal to 1/2. I want to find when sine 2 theta is equal to 1/2. So what I can do to solve for theta, I'm now just going to divide every term by 2. That then gives us an isolated, it isolates our theta for both of them. Now 5 pi over 6 divided by 2 becomes, 5 pi over 12 plus, and then the 2's is simplify, plus pi k. And then for our second equation, we get pi over 12 plus pi k. And the same thing still applies. K is an integer, where k is an element of the integers. Now again, these two radians is when sine is equal to a half. I'm trying to solve for theta though. So I set those two solutions equal to each other because I know this argument gives you 1/2, but I need this argument to give me 1/2 as well. So I set it equal to each other and I solve for theta. But I have to also apply it to my general portion. If this was no general solution, then I wouldn't need to add this plus pi k that gets simplified in the problem. Now, let's look at the part that I keep saying where what makes these problems more challenging is algebra. So where are we at? A, B, C, and then here is a perfect example of what makes these problems a little bit more challenging. Because if we were to rewrite this as 1 minus x squared, that hopefully reminds you that this is the same as 1 squared minus x squared, which would become 1 minus x, 1 plus x, because it's the difference of squares. So that's what I mean, where we have to introduce some algebra, right? Some factoring skills. And it makes it difficult because there's this sign involved. But instead of writing x, we write 1 minus sine theta is equal to 1 plus sine theta, which is the same situation that we have written here. 1 minus x, 1 plus x. Let me write that a little bit neater. And now you have to remember from algebra the zero factor property. So make a quick note. If we remember the zero product property, that would be, it said if a times b was equal to 0, then we will take a, set that equal to 0, or b will equal 0. So each factor, we take each factor and set each one equal to 0. So we make two separate equations. This is all from algebra. Or 1 plus sine theta equals 0. From the first equation, that's going to become sine theta is equal to 1. Or from the second equation, it's going to be sine theta equal to negative 1. And where does this happen? Well, if we make our little circle to help us reference, you have to remember this point up here, this terminal point, is 0 for the x, but 1 for the y. This point down here was 0 for the x, but negative 1 for the y. Now, at first glance, your brain is probably thinking, okay, at pi over 2, and then 3 pi over 2, right? And then, oh, we become robots and then we start just always writing plus 2 pi k plus 2 pi k, but we're not thinking about what's happening here. And what I'm saying is, if we look at these two solutions, yes, there's two separate equations, but if you notice, to get from one solution to the next, luckily, that distance is exactly pi. So I can go from pi over 2 to get to 3 pi over 2 by just adding pi. And I can do the same thing to go right back. I can add another pi or subtract pi. Either one, depending what direction you're going. Right? We can either add or subtract by pi. And we're going to get to that exact same place. We did not do this for our previous examples because there's no way to add on the smaller angle the exact same to get to this back to the same position. But here, just because they're perfectly across from each other in a straight line, instead of writing this general solution with 2 repeating, I can generalize both of these to just saying pi over 2 plus pi k, and all that I'm taking out is 1. I don't need both of these, and I'm taking out this 2. Because taking out this 2, because I don't need to add 2 pi to get all the way around. I could just add pi, get to the next solution, add pi again, get to the first solution, and then second, first, second, first, second, first. And you can do that forever. Is a nice thing. Right? And we just have to get creative on how we do our examples, right? Recognizing when you can use these factoring techniques, right, that you did in algebra, thinking about what your general solution would look like. And just to give you a quick example of a different equation, let's say sine theta is equal to cosine theta. Sorry, sine theta times cosine theta is equal to cosine theta. But let's say if I'm only looking for solutions between 0 and 2 pi. So here I'm not looking for a general solution. I only want the thetas that make this true. Well, we have to rely back to this 0 factor property where we actually want our equation to be set equal to 0. And you can move either side to left or right, but because this side's bigger, I will move cosine to the left side and I'll subtract it on both. But that doesn't cancel anything. That just moves everything over to one side. That'll allow me to start thinking of how to apply my 0 factor property. Well, the idea is you're going to set each factor equal to 0. Well, when you see two terms that have the same factor, hopefully we remember what GCF is, right? Factoring out the GCF here, which is cosine, will leave us with sine theta. And when you factor everything out of a term, there's always a factor of 1 left behind. And then you can take each one of these factors and set it equal to 0. Now for cosine of when cosine is equal to 0, we know that happens, well, either at 0, at cosine is 0 at pi over 2 or 3 pi over 2, which is very similar to this solution. So that means I can just write instead pi over 2 plus pi k, where k is an element of the integers. And that allows for this general solution. And actually, I'm getting carried away. I don't need all of this. Right? Sometimes you just start acting like a robot. I only want the solutions between 0 and 2 pi. So it happens at pi over 2 and at 3 pi over 2 because these solutions are unique. The pi k was helping generalize how to get every one of these solutions. But I only want the solutions within one full rotation, and these are those solutions. Now this next equation, with moving everything over, right? I'm trying to find, okay, when is sine theta equal to 1? Now, you might be tempted to put this 3 pi over 2 like the previous one, but it only happens at pi over 2, which that is already a solution to this equation. So when you write your solution set, right? If you remember, some teachers prefer you to write your answers in a solution set. So they'll write braces. And your solution is just pi over 2 and 3 pi over 2. I wouldn't add an additional pi over 2 because it's already included in this first equation, and this is one overall equation. Again, the main idea here is isolate your variable, find the radian or degree that corresponds to that terminal point, and think about what other position will give you this exact same terminal point, and how far apart are they from each other. Do I need to add 2 pi, or do I need to just add pi to get to that same exact solution? So hopefully these weren't too complicated. Again, what's going to make these tricky is remembering how to use your algebraic skills. So I'll upload this one and give you some practice.